Good evening, my students, especially the candidates. You are most welcome in our today's class, and today I'm going to look at a topic in chemistry called radioactivity. This is the last topic in Form 4, in our chemistry syllabus textbook. And in as far as this topic is concerned, we are first going to look at the structure of an atom as we had previously looked at in our last lesson. And I must have mentioned this in that lesson. I must have said that this can be a structure of an atom where this can become our nucleus or the central region of this atom. And we have what you call energy levels. Energy levels are the regions that are found around our nucleus. So I've talked about this one as our nucleus or the central region of this atom. I've talked about these regions around this nucleus referred to as energy levels. And of course, an atom is the smallest particle of any element which can take part in a chemical reaction. This can be an atom and it must be the smallest particle of an element. If I will always take this as my element, which is a pure substance. We said this in our last lesson, that an element is a pure substance that cannot be split into simpler substances by chemical means. Within the element is an atom, which is now going to be the smallest particle of an element but can take part in a chemical reaction. So this is our element, which is a pure substance that you cannot be able to split into simpler substances by any chemical means. And within that element is an atom, which is the smallest particle of that element and can take part in a chemical reaction. So this smallest particle of this element is able to get magnified or enlarged using a microscope, and its structure is supposed to look like this. In as far as this atom is concerned, the central region of that atom becomes the nucleus, and the regions around this nucleus are referred to as energy levels. An atom has mainly three particles, for your information. The first particle is called a proton, and protons are positively charged. The second particle is called a neutron, and a neutron is neutral. It has no charge. And the last particle is an electron, and electrons are negatively charged. So protons and neutrons are found in the nucleus. Then electrons are found in the energy levels. To proceed from there, you should also note this. You should also note that if an element is atomic number 12, and that obviously must be an element called magnesium. And this element ends up having an electron configuration or an electron arrangement of 2 to 8 to 2. These electrons can give us what we call an electron arrangement. That is to tell you that the first energy level can have 2 electrons, okay? Then the second energy level can have 8, so you have 1, 2, 3, 4. Then we have 1, 2, then 3, 4. Those are 8. So we have the first energy level having 2, 1, 2. The second energy level having 8, 1, 2, 3, 4, 5, 6, 7, 8. Then the last energy level having 2 electrons. So the first 2 electrons, the second 8 electrons, and the last 2 electrons. Okay, so to proceed forward, when an atom takes part in a chemical reaction, the reaction it can take part can either be a nuclear reaction or a chemical reaction. So we've said this atom can take part in a reaction. The reaction it can take part can either get called a nuclear reaction or a chemical reaction. To begin with this second one, which is a chemical reaction, you should note this. A chemical reaction only involves electrons. But a nuclear reaction can occur from within the nucleus and can involve protons and neutrons. Just take note of that. Chemical reactions will always make use of the electrons, and nuclear reactions will always make use of protons and neutrons. That's there'll be a big difference between the two reactions that we've actually just mentioned in our discussion here. I've said the nuclear reaction can involve protons and neutrons, and chemical reactions involve electrons. For example, if I have an element like this, which is capital M small g, referred to as magnesium, and it has an electron configuration of 2 to 8 to 2. And maybe there's another one that has an electron configuration of 2 to 1. As an example, this is lithium. And then we have another one that has an electron configuration of 2 to 8 to 3. And these can be aluminium. So if an element has 1 electron in the outermost energy level, or 2 electrons in the outermost energy level, or 3 electrons in the outermost energy level, this element ends up reacting by losing. So the element ends up reacting by losing. We are still going on with our topic, which is radioactivity, and as per what I had previously noted down, I had said previously that an atom, being the smallest particle of an element, can take part in a chemical reaction. And in that case, if you have to actually consider this atom in this element, we can further be able to say that this atom of this element can actually take part in a nuclear reaction or a chemical reaction. And I have said that in a nuclear reaction, protons and neutrons are maximally considered, but in a chemical reaction, you only talk about the electrons. An example can be this: if you talk about a chemical reaction that only involves electrons. For example, lithium is number 3, magnesium is number 12, and aluminium is number 13 in as far as the atomic numbers are concerned. So the electron configuration of lithium is 2 to 1. The electron configuration of magnesium is 2 to 8 to 1. And the electron configuration of aluminium is 2 to 8 to 3. So if I say 2 plus 1, it must give me the number of electrons, which is 3, or the atomic number for that matter. Then if I talk about 2 plus 8 plus 2, it must be able to give me a total of 12, which is also the atomic number or the number of electrons. If I talk about 2 plus 8 plus 3, these 3 must add up to 13, which now serves as our atomic number or the number of electrons. So chemical reactions will always involve electrons or the atomic number. Why am I talking about the electrons or the atomic number? We've said that atomic number is the same as the number of protons, and the number of protons must always be equal to the number of electrons in an atom. I'm repeating this. The atomic number is the same as the number of protons, and the number of protons and the number of electrons in an atom of an element must always be equal. That is always to say that the atom of an element should always be neutral. For example, if I talk about lithium, and lithium is number 3, then that means the protons in this atom of this element called lithium is 3. So there are 3 positives. Then the electrons are also supposed to be 3. So you have 3 negatives. So the 3 positives will cancel out the 3 negatives so that the resultant charge is 0. So what am I saying? The number of protons in an atom of an element, of any element of course, must always be equal to the number of electrons. So the resultant charge of the atom is 0. The positives cancel out the negatives to end up giving us a 0 as the charge of an atom of an element. To proceed forward, you need to understand that if you have this as your atom, and within the nucleus of that atom are protons and neutrons. Then this particular nucleus that is characterized by a number of protons and electrons to the outside in that case, or the number of protons and neutrons to the inside should be able to get called a nuclide. That is to say that a nuclide is a particular nucleus of an atom of an element that is characterized by a particular number of protons and neutrons. I mentioned electrons because the number of protons and the number of electrons must be the same. Electrons are found outside the nucleus in the energy levels, but protons and neutrons are found inside the nucleus or the central region of this atom. So this particular nucleus that is characterized by a particular number of protons and neutrons is referred to as a nuclide. Is referred to as a nuclide. Okay, a nuclide is represented. A nuclide is represented by its mass number and atomic number. Look at this. I've said a nuclide is a particular nucleus of an atom that is represented or characterized by a particular number of protons and neutrons. Why? Because protons and neutrons are found inside the nucleus. So this nucleus, this particular nucleus that is characterized by these protons and these neutrons is referred to as a nuclide. And if you want to represent a nuclide anywhere, you're going to actually use 1, the mass number, 2, the atomic number. Let's use this example. I have an element X. X does not represent the actual symbol of this element I'm referring to. And this element is number 16. That means the atomic number is 16. Then I can come here and talk about 1, protons, then 2, neutrons, then 3, electrons. Then lastly, mass number. So I'll say, if the atomic number of this element X, I'm repeating, if the atomic number of this element X is 16, then that means the number of protons is 16. Why? Because the atomic number of an element is the same as the number of protons. Let me say, for example, the number of neutrons is 16 also, and obviously the number of electrons must be 16. Why? I've said this time in, time out, that the number of protons must always be equal to the number of electrons, but the number of neutrons can actually be different. But the proton number and the electron number must be the same. And how do I get the mass number? I'm going to say protons plus neutrons. And remember, mass number is also referred to as nucleon number. Nucleon number. Why? Whatever you're actually going to use to get the mass number is found in the nucleus. Protons are added to neutrons to give us the mass number. And because protons and neutrons are found in the nucleus, you can also refer to this as nucleon number. So nucleon number, why? We are actually summing up protons and neutrons. Found where? In the nucleus. That can also be able to get referred to as mass number. So in this case, I'm going to have the protons as 16, then the neutrons as 16. So my mass number becomes 32. My mass number becomes 32. So, for example, I want to represent this nuclide, which is the nuclide of X. We have said a nuclide must be characterized by protons and neutrons. But in this case here, to represent a particular nuclide, I'm going to use the mass number and the atomic number. So I'm going to put here the mass number and put here the atomic number. Mass number is written as a superscript. And in this case, X has a mass number of 32. So I'm going to write here 32. Then I'm going to put here the atomic number written as a subscript, which is 16. So a nuclide is a particular nucleus characterized by the number of protons and neutrons. And to represent this nuclide, I'm going to use mass number and atomic number. And I've told you atomic number is the same as the number of protons. So our mass number written as a superscript is 32. and the atomic number written as a subscript is 16. Okay. If you look at this, then that means you're going to say, for example, that X or element Y can have this 37, okay, and 17. And an atom of the same element can as well have 35 and 17. That is to say that the mass number of this nuclide is 37 and the atomic number is 17. For this other case, the mass number of this nuclide is 35 and the atomic number is 17. So, in that case, these are atoms of the same element. They have the same atomic number, but their mass numbers are different. They are able to get referred to as isotopes. What are isotopes? Isotopes are atoms of the same element. These are two atoms of the same element, Y, because this is Y and this also Y. So these two atoms must be of the same element because they have the same letter. And these atoms of this same element, which is Y, have the same atomic number, but their mass numbers are different. Why are their mass numbers different? Because the number of neutrons is different. For example, here the number of neutrons is 20. How do I get the number of neutrons? It is very easy. I'll just say mass number minus atomic number, or the number of protons. So the number of neutrons is 20. How then do I get the number of neutrons here? I'm going to have the number of neutrons as 18. I take the mass number, which is 35, less the atomic number or the number of protons, which is 17. So the number of neutrons is 18. So atoms of the same element with the same atomic number but different mass numbers due to the difference in the number of neutrons. Okay, for example, these are isotopes. There are two. The first isotope, the second isotopes. Atoms of the same element with the same atomic number, different mass numbers due to the difference in the number of neutrons. And the abundance of these isotopes will differ. For example, isotope 35 is 75% abundant. Then isotope 37 is 25% abundant. That is to tell you that isotope 35 is more abundant than isotope 37. So the abundance of atoms of the same element will actually be able to differ. So if I look at these two, there are atoms of the same element referred to as isotopes, and their abundance in our environment is differing. Okay, you can actually be able to talk about nuclides. And I've said a nuclide can only be able to get characterized by two very important particles. And if this is our atom, and we talk about this as our nuclide, it must be able to get characterized by the proton number and the number of neutrons. So this nuclide is carrying protons and neutrons. It can either be stable or unstable. It can either be stable or unstable. So in other words, nuclides or a nucleus having protons and neutrons can either be stable or unstable. And the stability or the instability of a nuclide or a nucleus characterized by protons and neutrons is determined by the neutron-proton ratio. So I want to know whether this nucleus that has protons and neutrons either being stable or unstable. I'm actually going to talk about the neutron-proton number in terms of the ratio. So the neutron-proton ratio, neutron-proton ratio. For example, if I talk about calcium and I have to place here 20 or place here 40, then I place here 20. I'm going to have the number of protons as 20 because the one written as a subscript is the number of protons, which is also referred to as the atomic number. Then I'm going to have the number of electrons as 20 because I've told you the number of protons and the number of electrons must be the same. Then we can talk about the number of neutrons, which is also 20. and our mass number is going to be 40. So to proceed forward, we are going to say that the neutron-proton ratio can tell us whether this nucleus of this atom is stable or unstable. So I'll say that the neutron-proton ratio of calcium nucleus is going to be 20 divided by 20. That is the neutron number, which is 20, and the proton number, which is also 20. So the ratio becomes 1 to 1. The ratio becomes 1 to 1. So it is always advisable that for an atom to have a nucleus which is characterized by protons and neutrons, getting referred to as a nuclide, being stable, should have a neutron-proton ratio not more than 1.6 to ratio 1. I repeat, for any atom to have a nucleus characterized by protons and neutrons with a ratio of 1.6 to 1 or less is always regarded to be stable. But any nuclide or a nucleus having a particular number of protons and neutrons ending up having a neutron-proton ratio more than 1.6 to 1 is always regarded as being too large and unstable. You see? So if I have a neutron-proton ratio of 1.6 to 1 for a particular nucleus, that nucleus becomes stable. But any neutron-proton ratio that is more than 1.6 to 1 is always regarded to be too large and unstable. And something must be done for it to actually attain its stability. Something must be done for it to attain its stability. So the unstable nuclide normally undergoes some changes for it to become stable. Imagine you have this case here. You have an atom of an element, and there is a nucleus here that has, let's say, 180 against 30. Let's use that as an example to be able to better explain this. So you have actually been told that maybe the proton number is 120, or let's say 180, and let's say the neutron number is 300. So you want to get the neutron-proton ratio and see whether this atom is stable or unstable. We shall come here and say the number of neutrons 300 divided by the number of protons 180. Let's simplify this. This 0 and this 0 will cancel. Then we shall say 6 there, 3, 6 there, 5. Okay, so we can further divide this and have 3 there once, 3 there, that is 1.67 rounded off to 2 decimal places. So that means that now our neutron-proton ratio is going to be, this is our neutron ratio, 1.67, then our proton ratio, which is 1. So let's come back here. Our neutron-proton ratio is to 1 decimal place 1.7 to 1. This atom is unstable. Why? Because any stable atom should have a neutron-proton ratio of 1.6 to 1. But this atom with 300 as the neutron number and 180 as the proton number has a neutron-proton ratio of 1.7 to 1. So it is actually above the recommended ratio in terms of stability of a particular nucleus. So the atom ends up having a nuclide characterized by this number of protons and this number of neutrons being unstable. And for it to gain its stability, for it to actually end up attaining its stability, it must be able to undergo disintegration, or it must be able to actually end up emitting radiations. So the radiations that can actually get emitted in terms of what you are referring to as the process of attaining stability should actually involve the following. Number one, an atom is having a nucleus. The nucleus is able to have protons and neutrons. The nucleus or nuclide is unstable. It must emit one, particles or radiations. So it must emit one, particles or radiations. Number two, it must emit energy for it to gain its stability. Obviously, I was having this number of protons and this number of neutrons. I am actually categorized as being unstable. I have emitted particles or radiations and energy. I end up becoming stable. I must end up yielding a particular nucleus with a different composition. You get the point? So I was unstable with a particular number of protons and neutrons. I end up disintegrating and producing particles or radiations and energy. I end up now forming a new nuclide or nucleus with a different composition. Now, what is now radioactivity? Radioactivity. From this explanation I've actually given in our previous discussion, radioactivity is the process where an unstable nuclide breaks up to yield another nuclide of different composition with emission of particles and energy. I repeat, radioactivity is a process where a very unstable nuclide ends up breaking up to yield another nuclide of different composition with emission of particles and energy. For example, I am having this and the proton number, let me talk about this as my nuclide. The proton number is 180 and the neutron number is 300. Then I end up having this as a new nuclide, maybe with 120 and 100. Okay, let's see. Then we are releasing also energy and particles. Okay, a process whereby a very unstable nuclide breaks up to form another nuclide with a different composition with the emission of energy and particles is called radioactivity. A very unstable nuclide with 180 and 300 as the proton number and neutron number breaking up or splitting to form another nuclide with a different composition of a proton number of 120 and a neutron number of 100 with emission of energy and particles is referred to as radioactivity. Okay, such a substance which undergoes radioactivity is referred to as a radioactive substance. A substance that undergoes radioactivity is referred to as a radioactive substance. A substance that undergoes radioactivity is referred to as a radioactive substance. We have actually previously said that sometimes you can find an atom X with maybe mass number of 300, maybe atomic number of 150, and another one with 150 as still the atomic number, and maybe 350 as the mass number. These are atoms of the same element called element X. They have the same atomic number, but their mass numbers are different. Because of these numbers, these isotopes are unstable. We said atoms of the same element having the same atomic number and different mass numbers are referred to as isotopes. So these isotopes are unstable. So they will undergo what you call radioactivity. So isotopes which are radioactive or isotopes which undergo radioactivity are called radioisotopes. isotopes which undergo radioactivity are referred to as radioisotopes. Isotopes which undergo radioactivity are referred to as radioisotopes. Now, what has happened here? There is a spontaneous disintegration of this. There is a spontaneous disintegration of this. There's a spontaneous breakdown of this. So the spontaneous disintegration of this nuclide is referred to as radioactive decay. Radioactive decay. Radioactive decay is the spontaneous breakdown or the spontaneous disintegration of this radioactive nuclide. The spontaneous breakdown, okay? The spontaneous breakdown or disintegration of this radioactive nuclide is referred to as radioactive decay. The spontaneous disintegration or the spontaneous breakdown of a radioactive nuclide is referred to as radioactive decay. The spontaneous breakdown of this nuclide is referred to as radioactive decay. So in other words, when someone talks about radioactivity, it is a nuclear reaction. Why? Because it is only going to involve the protons and neutrons in the nucleus. So it won't qualify to be called a chemical reaction because chemical reactions only involve electrons in the energy levels, and electrons are not found in the nucleus. So we can actually be able to say that chemical reactions will always make use of the electrons in the energy levels, but nuclear reactions will always make use of the protons and neutrons in the nucleus. So radioactivity involves the use of protons and neutrons, and that's why it becomes a nuclear reaction. So radioactivity is a nuclear reaction because it involves protons and neutrons in the nucleus. So that now takes us now to a different concept. We can now be able to give the differences between a nuclear reaction and a chemical reaction. Correct. A nuclear reaction and a chemical reaction. We've said a nuclear reaction takes place in the nucleus. Look at that. Takes place within the nucleus and involves protons and neutrons. Takes place in the nucleus and involves protons and neutrons. But now, this chemical reaction takes place to the outside of the nucleus, always making use of the electrons. Chemical reactions will always make use of the electrons in the energy levels. Chemical reactions will always use the electrons in the energy levels. So it does not involve protons and neutrons. Chemical reactions will always make use of the electrons in the energy levels, but not protons and neutrons in the nucleus. So it will always use what we call valence electrons. Valence electrons means the electrons in the outermost energy level. For example, 2 to 8 to 1. This becomes a valence electron. It's an electron in the outermost energy level that can allow this atom to take part in a chemical reaction. So atoms don't take part in chemical reactions using all the electrons. They only use the electrons in the outermost energy level, referred to as valence electrons. That's the first difference. This nuclear reaction can release a large amount of energy. A large amount of energy. Just try to imagine. An atom is very large and unstable, and it ends up disintegrating or breaking down to form another atom or another nucleus. There must be the release of a large amount of energy. We've said radioactivity is the process where an unstable nuclide breaks up to form another nuclide with a different composition. And in the process, energy and particles are released. So this process called radioactivity, which occurs within the nucleus, called now a nuclear reaction, will release a large amount of energy. So a large amount of energy is released in a nuclear reaction. But on the other hand, the heat released in a chemical reaction is much less. Heat released is much less. Heat released is much less. Or less energy is released in a chemical reaction. but a large amount of energy is released in a nuclear reaction. Now, try to imagine this is an atom, and the nuclear reaction occurring here is only involving protons and neutrons. And this is an atom as well. We have the protons and neutrons here, but they're not getting used in this chemical reaction. So we're only going to use the electrons, called the valence electrons, in the outermost energy level. So something else to note in as far as the differences are concerned. A proton and a neutron, or protons and neutrons in the nucleus, can allow us to have what we call a nuclear reaction getting discussed. So in this case, nuclear reactions are not affected by environmental factors like pressure and temperature. But chemical reactions are affected by environmental conditions such as pressure and temperature, or even the concentration of the reactants, or even a catalyst can alter the rate of a reaction. So environmental conditions like pressure, temperature, concentration, you see, catalyst, you see, surface area of the reactants can affect chemical reactions. But nuclear reactions are not affected by pressure, are not affected by temperature, are not affected by the concentration, are not affected by the catalyst, are not affected by the surface area or any other condition that can be found within our environment. Those are the three main differences between nuclear reactions and chemical reactions. To move forward, we are also supposed to look at types of radioactivity. Types of radioactivity. Types of radioactivity. Types of radioactivity. And there are two main types of radioactivity. Number one is natural radioactivity, and number two is artificial radioactivity. Natural radioactivity and artificial radioactivity. Natural radioactivity occurs when a radioactive nuclide. We begin with the natural radioactivity. Types of radioactivity: natural radioactivity and artificial radioactivity. With natural radioactivity, you'll find a radioactive nuclide or a very unstable nuclide splitting spontaneously to yield a new nuclide with the emission of radiation and energy. The emission of radiation and energy. That is what we refer to as natural radioactivity. It's very simple. A radioactive nuclide or an unstable nuclide or nucleus splitting spontaneously to give rise to a new nucleus or nuclide, but with emission of radiations and energy. For example, I can talk about this. This is 234 as the mass number. Let's say this is thorium. Thorium as an element with mass number 234, capital T, small h as the chemical formula of that element, being able to actually split to form another nucleus with atomic number 229. Look at that. A radioactive nuclide splitting to form another nuclide with emission of energy and radiations. That's what we refer to as natural radioactivity. Or sometimes you can have an atom like uranium having a mass number of 238, spontaneously splitting to give rise to another nuclide with the mass number 234. This is uranium and this is thorium. This is referred to as natural radioactivity. A very unstable nuclide splitting to give rise to another nuclide that has a different mass number. But together with this, you can also emit energy and radiations. Correct. When someone talks about artificial radioactivity, it occurs when a large stable nuclide. It is a large but stable nuclide. The difference is, in natural radioactivity, the nuclide is unstable. You get the point? And it being unstable, it ends up splitting spontaneously, yielding a new nuclide with the emission of radiation and energy. In this other case, you'll find a large but stable nuclide, let's say for example 208 for lead, a large stable nuclide, this for lead, capital P small b, a large stable nuclide like that of lead getting bombarded with a fast moving high energy particle. Okay, so this is a large and stable nuclide of lead getting bombarded by a fast moving high energy particle. Look at that. A large stable nuclide of lead getting bombarded by a fast moving high energy particle. And in the process, you'll end up having this large stable nuclide splitting to form smaller nuclei. Splitting to form smaller nuclei, but again, energy and radiations are also emitted. So, artificial radioactivity involves having a large stable nuclide, for example for lead, getting bombarded by a fast moving high energy particle and making it to end up splitting into smaller nuclei with emission of energy and radiations. I hope you have actually enjoyed our lesson. Thank you so much. Let's meet in our next video. Welcome again to our today's lesson, and to proceed from where we had stopped, I had initially talked about a radioactive nuclide being able to get bombarded by a fast moving high energy particle to end up splitting and giving us two smaller nuclei. Nuclei is the plural of nucleus. So one radioactive nuclide or nucleus getting bombarded by a fast moving high energy particle, so that this nuclide or this atom in general ends up splitting to give us two smaller nuclei. The first nucleus, the second nucleus. Of course, the different nuclear composition or constitution in terms of the number of protons and the number of neutrons. To accompany these two nuclei, which are produced from this radioactive nuclide, we also have energy and radiations. This energy that gets produced here can get harnessed and put into very purposeful applications in our environment, such as this production of electricity, where the energy that gets produced here can be able to actually heat the water. The water forms steam. The steam can turn turbines, and this can be able to generate electricity in a hydroelectric power station. But now, let's come back and look at the radiations produced when a radioactive nuclide ends up splitting. So, types of radiations produced in a radioactive emission, types of radiations. So the first type of a radiation that gets produced in this radioactive disintegration or spontaneous breakdown is called an alpha particle. It is symbolized as this, as an alpha particle. The second radiation is called a beta particle, symbolized as this, beta particle. And the third radiation that gets produced during this radioactivity is called a gamma radiation. And its symbol is that. So we have an alpha particle, a beta particle, and a gamma emission. Those are the three main types of radiations that are always able to get produced when a radioactive nuclide undergoes disintegration or spontaneous breakdown to form other nuclei with emission of energy. We shall be able to look at some of the features of each and every radiation getting produced in this case. And I'm going to begin with the alpha. For the first purpose of us understanding this, you can be able to actually understand that this alpha particle is abbreviated as that. That's the symbol of alpha particle. And this alpha particle is just a helium atom, a helium nuclei, a helium atom or an helium nuclei. And in this case, it is actually able to chemically appear as this. So you have capital H small e as the chemical formula of helium with a mass number of 4 and with an atomic number of 2. This helium carries a charge written as 2 positive. So the oxidation number is +2. We actually said in our last lesson that when you are capturing the charge on an atom of an element, begin with the number or the numeral, then the charge. But if that same charge is able to get captured in form of an oxidation state or number, begin with the charge, then capture the number later. So you can have an oxidation number of +2, but a charge of 2 positive. The oxidation number begins with the charge, but the charge begins with a number. That's the difference. So the charge is positive, and that means it's actually going to be 2 positive, but the oxidation number is +2. So helium particle or helium nuclei is an alpha particle. So if someone says a radioactive nuclide has emitted a helium particle, or a radioactive nuclide has emitted an alpha particle, just know a helium particle has been emitted. And in that process, it must have a mass number of 4 and atomic number 2 with a charge of 2 positive. What did I say? A radioactive nuclei or radioactive nuclide is represented using mass number and atomic number. So the mass number is 4 and the atomic number is 2. So the helium particle becomes an alpha particle that has a mass number of 4 and an atomic number of 2. You see, of all the 3 radiations, the alpha becomes the heaviest of all. Of all these 3, the alpha, the beta, and the gamma, the alpha becomes the heaviest of the 3. So alpha particle is a helium nuclide. It has a mass number of 4 and an atomic number of 2 with a charge of 2 positive. Of the 3, it is the heaviest. It is the heaviest, having a mass number of 4. Okay, something else about this alpha particle. You can actually realize that the alpha particle is able to have a low penetrating power. It has a very low penetrating power. It has a very low penetrating power. A very low penetrating power. That is to mean if this is my alpha particle and I allow it to actually come from a radioactive substance such as lead, then you can actually end up having this alpha particle getting blocked by a thin sheet of paper. Thin sheet of paper. Just imagine a thin sheet of paper. This is a radioactive substance, a radioactive nuclide, being able to emit an alpha as a radiation or as a particle, which is a helium nuclide. When this particle is emitted from this radioactive substance, this particle gets blocked by a thin sheet of paper. So it has a very low penetrating power. So they do not pass through a sheet of paper. You see, so they have just a range of a few centimeters in air in terms of their penetration. They have a very low penetrating power. So they can get blocked by a thin sheet of paper. Can get blocked by a thin sheet of paper. So I have said in the first case that if you're talking about an alpha particle, it must be a helium nuclide. And a helium nuclide is positively charged, number 1. It is the heaviest of the 3 radiations, having a mass number of 4 and an atomic number of 2. We've said it being very heavy, then that means it has a very low penetrating power, just being able to pass through a few centimeters in air and getting blocked by a thin sheet of paper. So you can be able to see its ability to get deflected in an electric field. For example, if I can be able to have this as my positively charged plate, and this becomes my negatively charged plate. Where is this alpha particle going to get deflected? It is carrying a positive charge. So, like charges repel and unlike charges attract. So that means it is going to get deflected on the negative plate in our electric field. Look at that. An alpha particle, being the heaviest with a mass number of 4 and being positively charged or having a charge of 2 positive and having a very low penetrating power, getting to that point of only having few centimeters getting covered and being able to get blocked by a thin sheet of paper, can end up getting deflected to the negative terminal, to the negative plate in an electric field. Why? Because it carries a positive charge. Carrying a positive charge makes it to get deflected to the negative plate in our electric field. So they are positively charged, so they get deflected to, or they get attracted to, the negative plate in that electric field. So they are not very light, they are very heavy. So they are very slight deflections. They have very slight deflections. Why? Because their heaviness will make them to move at a very slow speed and make them to slowly get deflected to a very smaller extent towards the negative plate in that electric field. And in terms of ionizing, we can be able to actually come here and say they have a greater ionizing power or ionizing effect. Of the 3 radiations, they have a very high ionizing power. They produce a large number of ions. For example, you have 4,2 He with the 2 positive. And remember, they have a positive charge of 2. So just to imagine, you are actually having this as your ions. And these ions are getting produced by the helium or the alpha particle. And they find their way into the air. You can try to imagine the ionizing effect they are going to have to these particles in the air. All these particles get ionized because of these positive ions getting produced by this helium particle. So they have a very high ionizing power. They produce a large number of ions. So that as they pass through gases, let's say these are gases, and due to their slow speed and high charge, this makes them to have a greater contact with the atoms for a longer time. I repeat, alpha is the heaviest with a mass number of 4 and an atomic number of 2. It is a helium particle with a charge of 2 positive. Having a charge of 2 positive makes it to get deflected to the negative plate in the electric field. It is actually able to get deflected to a smaller extent. Why? Because it is very heavy. It is the heaviest with a mass number of 4. To add on that, we are saying that it has a very greater ionizing power. Why? Because it carries a very big charge. It carries a greater charge. So, 1, it has a bigger charge. 2, it is very heavy. So as it moves in the air, what happens? It is heavy and having a greater charge, making it have a longer time in terms of its contact with target atoms in the air. It is very heavy, and with a bigger charge, it ends up moving very slowly. And as it moves very slowly, it has a longer time in as far as its contact with the target atoms in the air is concerned. So the longer time it has, in as far as its contact with the target atoms is concerned, it ends up having a higher ionizing power. So 3 properties to remember in as far as alpha particles are concerned. We've said an alpha particle is a helium nuclide that has the largest mass, which is 4 of the 3 radiations, and an atomic mass of 2. It has the highest charge. And it's positively charged. So when actually allowed to pass through an electric field, it gets deflected or attracted to the negative plate in the electric field. Being heavy, it has a smaller deflection or attraction. It only covers a shorter period in the air. It only covers a shorter distance, a few centimeters. Why? Its heaviness will make it to cover a shorter centimeters or a few centimeters in the air. And in that process, it gets blocked by a thin sheet of paper. And to move forward, we've said it having a bigger mass and being heavy for that matter, and having a slightly bigger charge, which is positive 2. It will end up moving slowly and covering few centimeters in the air. And in the process, it will end up having a longer time in contact with the target atoms of gases in the air. The longer time it has, in as far as its contact with the target atoms of the gases in the air is concerned, will make it have a high ionizing power. It ionizes those atoms. It makes those ions to become charged. It makes those atoms to become further charged. So its heaviness and its bigger charge and its longer time in contact with those atoms of those gases will make those atoms of those gases to become charged. So it has a high ionizing power when allowed to find its way into the air. And the second radiation is called a beta particle, abbreviated as that or symbolized as that. And this beta particle is able to get produced when a neutron is emitted from the nucleus. Look at that. So let's say this is our neutron, and this neutron is leaving the nucleus. Look at that. This is a neutron with a mass number of 1 and no atomic number. Look at that. And this neutron is splitting. On splitting, the neutron ends up forming a proton with a mass number of 1 and a proton number of 1. And further, it can also be able to now form what you call an electron with no mass number but now negatively charged. Look at that. So this is a neutron from the nucleus getting split to form a proton again within the nucleus, and also an electron is released. So a neutron with a mass number of 1 and no atomic number is getting split. On getting split, it forms a proton with a mass number of 1 and the proton number is able to get given as 1. It has no mass number, but it has a negative charge of -1, and it is actually able to get called an electron. For this case, you're going to realize that the mass numbers 1 plus 0 on the proton and the electron can add up to the mass number of the neutron. So 1 plus 0 is 1. Then the atomic numbers of the proton and the electron should also add up to the atomic number of the neutron. 1 plus -1, it gives you 0. So basically, this one becomes our beta particle. So in other words, a beta particle is an electron released when a neutron splits. A beta particle is an electron released when a neutron in the nucleus splits. So it's not an electron in the energy levels. It is a neutron in the nucleus splitting to form a proton and that beta particle or that electron. And that beta particle, which is an electron from the nucleus, when a neutron splits, has a mass number of 0 and it is negatively charged. Look at that. It is now going to be the second lightest because we've talked about the helium that has a mass of 4 and of course an atomic number of 2 and is actually able to have a charge of 2 plus. So some of the differences to capture in these two is this. It is the heaviest with a mass number of 4. It is the second heaviest, of course, with a mass number of 0. It is positively charged. It is negatively charged. It is an alpha particle or a helium nuclide. It is an electron released from the nucleus when a neutron splits. Look at those differences. Something else to note is this. This one is able to become the second in terms of penetration. Look at that. The second in terms of the penetration. That is to tell you that this one is very, very, very heavy. It only covers a few centimeters in air. It is easily blocked by a thin sheet of paper. So it is the weakest in terms of penetration. This is the second particle to talk about in terms of penetration. It is able to pass through, let me say this is actually a radioactive substance like uranium. It is actually emitting a beta particle. Look at that. The beta particle can pass through a thin sheet of paper. Look at that. But can get blocked by an aluminium foil. See, so this is a thin sheet of paper. But this is an aluminium foil. An aluminium foil. So, a beta particle or an electron emitted from the nucleus on a neutron's plates is better in terms of penetration. How? It can pass through a thin sheet of paper that gets to that point of blocking an alpha particle, but can now further be able to get blocked by an aluminium foil. Remember, an alpha particle gets blocked by this aluminium foil, and that means it can further as well be able to get blocked by this thin sheet of paper. So if a thin sheet of paper blocks this alpha particle and the beta particle penetrates the thin sheet of paper, then the beta particle is better in terms of penetration. So it actually passes through the thin sheet of paper that blocks the alpha particle but gets blocked by that aluminium foil. So it has a better penetrating power. A better penetrating power in terms of passing through the thin sheet of paper that blocks the alpha particle. So it has a higher penetrating power than the alpha particle. A higher penetrating power than the alpha particle. Higher penetrating power than the alpha particle. Higher penetrating power than the alpha particle. Now, in terms of deflection, let's come back to this deflection. You see, if you talk about a beta particle, look at that, a beta particle, which is an electron, you'll realize that the beta particle is actually an electron which is negatively charged. But I've talked about an alpha particle being a helium, which is positively charged. So, this beta particle, which is an electron with a negative charge, gets deflected to the positive plate in the electric field. Why? It is carrying a negative charge. So the negative attracts the positive, or the negative is attracted to the positive. In other words, if you look at these two, you should actually realize that this one is lighter. It has no mass number, but this is very heavy with a mass number of 4. So it has a smaller extent of deflection. Let me just reduce this to this point. That makes sense. So it has a smaller extent of deflection because it is very heavy. It has a greater extent of deflection because it is very, very light. Look at that. A smaller extent of deflection because of its heaviness, a greater extent of deflection because of it being light. So get the difference in terms of where it gets deflected to the positive plate to the negative plate because of carrying different. Coming back to the beta particles, just to proceed from where we had left, we've said a beta particle is an electron that has no mass number, but it has a negative charge. You know, if you compare this with an alpha particle, which is a helium nuclide, you'll realize that a beta particle has a smaller charge, but a helium or an alpha particle has a bigger charge. So this one has a lower ionizing power because it produces few ions. So I have -1, then I have +2. Let's see. This is negatively charged, that's now the beta particle. This is positively charged, that is the alpha particle. Between these two, which one will produce more ions? This one has a bigger charge, so it produces more ions. This is able to have a smaller charge, so it produces few ions. Look at that. So the few ions it produces and the lightness it has, and now being able to move quickly or faster, will make it to actually move quickly in the air. That is number one. And it having a smaller charge will actually end up making it to have a smaller contact with atoms of the gases. I've said number one, it has a smaller charge. Number two, it is very light, so it moves quickly. So it will have a shorter period of its contact with the atoms of the gases it finds in the air. So it will have a lower ionizing power. When you come back here, we have said it has a mass number of 4 and the charge is bigger, so it produces more ions. So the more ions it produces and the heaviness that makes it to move slowly can make it to have a longer period of contact with atoms of the gases. So it has a greater ionizing power it has a smaller ionizing power because of the smaller charge and the lightness that makes it to move quickly. So having a smaller period of contact with the gases in the air or with the atoms of the gases in the air. Okay, something else is this. You should also note that we have the last type of particle called the gamma particle, with the gamma particle abbreviated as that or symbolized as that, is just a radiation that is produced when other radiations are produced from the nucleus. They don't get produced on their own. So when a beta is released, an alpha is released, is when you can also release a gamma radiation. So it is actually able to accompany the emission of gamma, beta, and alpha. So when you release a beta particle and release an alpha particle, expect also to produce gamma radiation. A gamma radiation has no mass number, has no atomic number. Look at that. Number two, it has no charge. So you can try to imagine. It has no mass number, it has no atomic number, it has no charge. So it does not cause any form of ionization in the air. It does not carry any charge, so it does not cause any form of ionization in the air. No atoms of the gases in the air get ionized by these gamma radiations because they don't carry any charge, whether positive or negative. And to make these things work easier for us, we are going to actually say that they are high energy rays. They are high energy radiations. They do not have an electrical charge. They don't carry a positive charge, and as well they don't carry a negative charge. And if say they don't get emitted on their own, they must be able to accompany the emission of alpha and beta particles. Gamma rays have the highest penetrating power. If this becomes a radioactive substance and it ends up producing a gamma radiation, it will have the highest penetrating power. It won't get blocked by a thin sheet of paper. As well, it won't get blocked by an aluminium foil. But can only get blocked by a thick lead block. A thick lead block. So, of the three radiations, it has the highest penetrating power. Of the three radiations, it has the highest penetrating power. Of the three radiations, it has the highest penetrating power. It can pass through a thin sheet of paper that was blocked by an aluminium oil. It can get blocked by only the thick lead block that is actually even more heavier than these two. So this gamma radiation can actually be able to only get blocked by this thick lead block. It passes through the thin sheet of paper that blocked the alpha particle. It passes through the aluminium foil that blocked the beta particle and can only get further blocked by this thick lead block. So it has the highest penetrating power. So then that is to say that they can only get blocked by what? The thick lead block. Deflection in the electric field, they actually end up getting to that point of just passing through the electric field. Why? They do not carry any charge. And if they don't carry any charge, they are not attracted to the positive plate and neither are they attracted to the negative plate. They actually pass through this field undeflected to any of those two plates because they don't carry any charge. They don't carry any charge. So they are unaffected when they pass through an electric field. That is to actually mean they do not end up getting deflected to any of those two plates. And to actually finalize on this, we are going to say that they have a very, 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 very low ionizing power because they do not carry any charge. The highly ionizing particles are the alpha particles with the highest charge of +2. The second highly ionizing particles are the beta particles with a charge of -1. And the lowest in terms of the ionizing power are the gamma radiations with no charge and no mass number and no atomic number. Now, you'd also want to know more about half-life. Radioactive substances are actually getting to that point of decomposing, disintegrating, or breaking down spontaneously. So when someone says half-life, which is a very important concept, half-life. Half-life means the time taken for a given mass or number of a nuclide to decay to half its original mass. The time taken, for example, let me say there's a radioactive substance which is 40 grams. Then it decomposes or disintegrates or splits or breaks down to give another nuclide with 20 grams. And maybe it has taken 10 days. Look at that. The time taken, that's now 10 days, for a radioactive substance or nuclide to reduce to half its original mass is what we refer to as half-life. The time taken, now 10 days for this case, for a particular radioactive substance or nuclide to reduce to half its original mass is what we refer to as half-life. The time taken for a radioactive substance to reduce to half its original mass is what you call half-life. Time taken for a radioactive substance to reduce to half its original mass is what we refer to as half-life. Let's use this example. You have been told that a substance is 400 grams and its half-life is, for example, 10 days. You see, so someone is asking you to give the mass of this substance after 30 days or even after 40 days. So 40 grams must reduce to 200 grams because this should be the time taken for this radioactive substance to reduce to half its original mass. It further reduces to 100 grams and further reduces to 50 grams. Look at that. So it has taken 10 days as the half-life, 10 days further, and then 10 days further. So if the original mass of a substance is 400 grams and it starts to disintegrate or split or break down and its half-life is 10 days, how many grams will it end up with after 30 days? Let's do this. Put here the original mass, which is 400 grams. Allow it to actually split or disintegrate to half its original mass in 10 days. That will give us 200 grams. Further, allow it to reduce to 100 grams, half its original mass for 10 days. Then further allow it to reduce to 50 grams, half its original mass in another 10 days. The three are going to give us 30 days. So in 30 days, the 400 grams will reduce to 50 grams. The half-life is 10 days, and the original mass is 400 grams. It reduces to 200, further reduces to 100, further reduces to 50. In 10 days, 10 days, 10 days. Those are 30 days. After 30 days, the mass reduces to 50 grams. Some will use the formula. They'll say the final mass or mass after time t will be equivalent to the original mass, look at that, into half. You get the point? Then you say raised to time over half-life. This is the final mass after splitting, disintegration, or radioactivity. This is the original mass before disintegration into a half raised to the total time taken over the half-life for that thing to reduce to half its original mass. For example, we want to get the final mass, Nt. We shall say is equals to, using this example, the original mass is 400 grams. So we shall say 400 grams into a half, close brackets. What is the total time given? They have told us to get the mass after 30 days. So the t can actually take 30 days. So we shall say 30 over what is our half-life? Our half-life is the time taken for that substance reduced to half its original mass, and that is 10 days. So we shall say over 10. Remember, this is a power. So we're going to have final mass Nt as 400 grams into a half raised to 3, because this 0 and this 0 will cancel. So the final mass Nt will be equivalent to 400 grams into 1 over 8. That is a half raised to 3 is 1 over 8. So the same as now the final mass getting given as 400 grams times 1 over 8. And that gives us 50 grams. So you can use this formula to be able to get to that point of understanding this concept very well. So the final mass Nt, mass after time t, should be equal to the original mass into a half raised to the total time over the half-life. Original mass is 400 grams. Original mass 400 grams. It is here. The original mass. Original mass 400 grams into a half raised to the total time taken, time given, 30 days. So we shall say 30 days. Then over the half-life, time taken for it to reduce to half its original mass, that is actually 10 days, you'll say over 10. So that's 0 and 0 will disappear, so you have a half raised to 3, which gives us, so 1 cubed is 1, 2 cubed is 8. So 400 times 1 over 8 gives you 50 grams. So after 30 days, the mass will reduce to 50 grams. After 30 days, the mass will reduce to 50 grams. Okay, this knowledge is very, very important. Why? Because it can be able to help us understand how we can calculate the age of fossils. There is what we call the carbon-14 dating. It is called radioactive carbon-14 dating. I can know the age of fossils of both plants and animals. Why do you even talk about plants and animals? Because plants use carbon dioxide during photosynthesis to manufacture food. And that means they end up having carbon as an element in their structures. Animals solely depend on plants as a source of food. So they also end up having carbon in their structures. So if an animal dies or a plant also ends up ending its life, then you can determine the age of this plant or this animal by carrying out what we call radioactive carbon-14 dating. It can tell us the age of this remain of plants or animals. So you can use this knowledge in what we call radioactive carbon-14 dating. And it's actually abbreviated. We're actually able to get estimated as 5,600 years, you see, for a particular carbon-14 element or substance in a dead plant or animal to decay to have the original mass. So let's look at nuclear reactions. So when you release an alpha particle from the nucleus, what happens to the mass number and of course the atomic number? Let's say we have an element like proactinium. Proactinium, and this proactinium has a chemical formula capital P small a. Let's say it has a mass number of 233 and atomic number 91, and the proactinium releases or emits an alpha particle. Then we shall have 4, then 2, then He. We shall say plus. Let's have actinium as the atom to be formed. Actinium. So we have proactinium with mass number 233 and atomic number 91. Proactinium emitting an alpha particle with a mass number of 4 and atomic number 2. This is a helium. So it forms an actinium. The mass number here is going to be 229. Why? 229 plus 4 must give us 233. Then the mass number is going to be 89. Why? 89 plus 2 gives us 91. Look at that. So proactinium emits an alpha particle. It forms actinium with the mass number 229 and atomic number 89. I've said these two mass numbers must add up with the mass number of the radioactive nuclide. These two atomic numbers must add up with the atomic number of the radioactive nuclide. Correct. Now, assuming you are also emitting a different particle, like let's say you have emitted a beta particle for that matter. You might have this. You have carbon-14. Look at that. And the carbon-14 emits a beta particle. You might form nitrogen. Look at that. Because a beta particle has a mass number of 0 and a negative charge. It's an electron, remember, from the nucleus. So now neutron is able to split. So it forms nitrogen. How does it form nitrogen? We're actually going to put here 14, because 14 plus 0 is just 14. Then you're going to put here which number? 7. So that we shall say 7 plus negative 1. It gives us 6. So when carbon-14 or radioactive carbon-14 with a mass number of 14, the atomic number 6, ends up emitting an electron or a beta particle, it ends up forming a new atom or nuclide, which is nitrogen. So that the mass numbers can add up to 14 and the atomic numbers can also as well add up to 6. So nitrogen is number 7 with atomic number 7 and mass number 14, formed when radioactive carbon-14 emits an electron. Correct. But now, unfortunately, is this. unfortunately, you are actually going to realize that when you have this as your radioactive nuclide, then you decide to emit a gamma radiation. You decide to emit a gamma radiation. Remember to note this: the mass number and the atomic number does not change. Why? Because gamma radiations are high energy radiations that have no mass number and they have no atomic number. So 14 plus 0, it just gives you 14. Then 6 plus 0, it gives you 6. So emitting gamma radiations does not change the mass number and the atomic number of the radioactive substances. And in that process, remember, a particular radioactive nuclide can emit several radiations. It can emit several alphas, can emit several betas, and can emit several gamma radiations. So at the end of the day, it forms what we call a radioactive decay series because it wants to attain stability. We have actually been told, for example, that if you have thorium, let's say you have thorium, this is our thorium, and the thorium has a mass number of 232 and an atomic number of 90, for example. If it emits an alpha particle, it can form radium. Look at that. If it further emits a beta particle, it can form actinium. If it emits a beta particle, for example, it can actually form another thorium. If it emits, let's say, an alpha, it forms another radium. Look at that. If it emits, let's say even another alpha, it forms Rn. If it further emits, let's say, for example, an alpha particle, it can form B. Look at that. If it emits another particle like alpha, it can form lead. Look at that. If it further emits another particle. So this is what we call a radioactive decay series, where a radioactive nuclide ends up emitting several alpha particles, beta particles, and maybe even gamma radiations. Its aim is to attain stability, to have its nuclide becoming stable, so that at the end of the day, we shall have the lead. We shall have the lead with a mass number of 208 and an atomic number of 82, being one of the most stable nuclides in our discussions. So this series, where a radioactive nuclide or a very unstable nuclide ends up emitting several radiations to attain stability, is what we refer to as a radioactive decay series. A radioactive decay series. Radioactive decay series. So it has to actually involve several emissions. An alpha, a beta, an alpha, an alpha, an alpha, an alpha. So several radiations are getting emitted from this radioactive nuclide for us to attain stability. So at the end of the day, we shall call this radioactive decay series. Radioactive decay series. To move forward, we may want to actually end up having a discussion over the types of nuclear reactions. One, we have what we call nuclear fission. Nuclear fission. Nuclear fission. Nuclear fission is the splitting process that a heavy nuclide undergoes when bombarded by a fast-moving neutron. Let me give you this example. Let me say, for example, you have uranium with the mass number 235 and the atomic number 92. This is uranium. Then this radioactive nuclide is getting bombarded by a fast-moving neutron. A neutron with a mass number of 1 and atomic number 0. What happens? It splits to give us barium with mass number 141 and atomic number 56. Look at that. And it also gives us Kr. I think you know this, krypton, with a mass number of 92 and atomic number 36. And it can also be able to produce 3 neutrons and energy as well. So look at this equation. Look at this equation. This is nuclear fission. And of course, the word fission means split. If someone says fission, that means split. Fission means split. So a nuclear fission means splitting. And that means a radioactive nuclide ends up splitting. A heavy nuclide, a radioactive heavy nuclide ends up splitting when it gets bombarded by a fast-moving neutron, a fast-moving high-energy neutron. And if it gets bombarded, it splits to form one barium with mass number 141, atomic number 56, to form two krypton with mass number 92 and atomic number 36, and it also ends up producing three neutrons. 1, 0 is a neutron, but there are three of them. Then also a large amount of energy is produced. So if you say 141 plus 92 plus 3 times 1, it must give you 235. Correct. So 141, those are the mass numbers, 92, that is 3. You get the point? So that means at the end of the day, you're going to actually end up having a total of 235, or rather you can actually have 236 as the mass number of uranium. Why? Because you'll come here and say 141 plus 92, that gives you 233. Then you shall say that's 141 plus 92, that is 233. Then 3 times 1, it gives you 3. So you end up having 236 as your mass number. At the bottom here, you have 56 plus 36. So 56 plus 36, that gives you 92. Then 3 times 0, that is just 0. So 92 plus 0 is 92. So 56 plus 36 plus 3 times 0 gives you 92. Then 141 plus 92 plus 3 times 1 should give you 236. Then plus this, so this 235, just okay. 235. Why 235? Because you're going to say 235 plus 1, that gives you 236. So you can just have your 235. So that 235 plus 1 gives us 236. So 141 plus 92 plus 3 times 1, that gives us 236. We shall come here and say 235 plus 1, that gives us 236. So these 3 should give us 236. Then these 2 should also give us 236. These 2 should give us 92. Then these ones should also give us 92. That's a nuclear fission, a nuclear fission, a nuclear fission. A radioactive nuclide, which is heavy and unstable, getting bombarded by a fast-moving neutron to give us 2 smaller nuclei. Look at that. To give us 2 smaller nuclei. And 3 neutrons are also produced with a large amount of energy. The other one is called nuclear fusion. Nuclear fusion. With the nuclear fusion, what happens is this. 2 smaller nuclei combine together when they're actually made to collide at high velocity. And this fusion results in the formation of a heavy nuclide. The process is also accompanied by liberation of a large amount of energy. For example, I can have tritium hydrogen. You know, hydrogen is actually radioisotopic. And in that case, that means it is actually able to exist in form of several isotopes. So we have what we call the tritium as an isotope of hydrogen. We have what we call protium and also deuterium. So this is a hydrogen with a mass number of 3. It gets called tritium as an isotope of hydrogen. This is called deuterium as also an isotope of hydrogen, the mass number of 2. We have the other one called protium with a mass number of 1. Okay. In that case, that means this is fusion, fuse or combine. That means 2 smaller nuclei are able to combine when they get bombarded with each other so that they can be able to give us a larger nuclide. For example, you're going to have 4,2He plus 1, 0 neutron plus also energy. So let me just look at this. This is the first isotope of hydrogen called tritium. This is the second isotope of hydrogen called deuterium. They are the 2 small nuclei we are referring to. They are getting combined when they get bombarded and they form a larger nuclide of a helium with a mass number of 4 and atomic number 2. A neutron is also going to be produced, and that can also get accompanied by production of energy. So a helium particle, a neutron, and some energy can also get produced. So let's see. 3 plus 2, that gives us 5. 4 plus 1 also gives us 5. 1 plus 1, that gives us 2. 2 plus 0, that gives us 2. So we produce a helium particle, a neutron, and energy is also produced in the process. And that means we can now be able to look at the similarities between. So I've talked about a nuclear fission. Fission to mean splitting. You pick a radioactive and stable nuclide, you bombard it with a fast moving neutron. What happens? It splits to give us two smaller nuclei with the different mass numbers and atomic numbers. 3 neutrons are also produced, and this is also combined by a large amount of energy in terms of production. I've said the mass numbers of the products must be equal to the mass numbers of the reactants. The atomic numbers of the reactants must be equal to the atomic numbers of the products. Now, we want to look at the similarities between nuclear fission and nuclear fission. Number one, in both cases, large quantities of energy is produced. You can look at this. There's production of energy here. There's also production of energy here. So in both nuclear fusion and fission, energy is produced. Energy is produced. Energy is produced. Number two, in both processes, it can result in what we call chain reactions. This might not be the end. We can further be able to split this and further form new nuclei with a new nuclear composition. This might not be the end. This can further be able to undergo several reactions to form smaller nuclei or even bigger nuclei. So in this case, this barium and this krypton can further split when bombarded by fast-moving high-energy neutrons to form even smaller and smaller nuclei. This helium can further combine with other smaller nuclei to form larger nuclei. So they all have to involve what you call chain reactions. In both cases, we only involve subatomic particles such as neutrons. Remember here, we've talked about this large nuclide getting bombarded by a neutron and you're producing neutrons. Here, we are combining two smaller nuclei to form a larger nuclei and we're producing a neutron. So we actually have to talk about subatomic particles such as neutrons in such a reaction. So they're actually able to get accompanied by neutrons. So in each case, neutrons as subatomic particles are produced. Neutrons as subatomic particles are produced. So the energy that we can be able to produce from here, this energy here and this energy here, can actually be able to get harnessed and converted into other forms of useful energy, such as electrical energy. And remember, the larger amount of energy produced in both reactions can be very destructive when misused, such as in the nuclear warfare. I'm saying this. In the nuclear reactions, nuclear fission or splitting or nuclear fusion or combining or fusing, we have to actually produce a large amount of energy. This energy can be harnessed and get converted into useful forms of energy like electrical energy. But if not well handled, the energy can be very, very destructive. In the two processes, we've said subatomic particles are also able to get produced, such as the neutrons. This nuclear fission produces 3 particles of neutrons. This produces 1 particle of a neutron. Those are the similarities between those two reactions. Now, what are some of the applications of radioactivity? For example, in medical application, you realize that we can be able to produce radiations such as the gamma radiations, which can actually destroy cancerous tissues. You get the point? So a patient gets exposed to the correct dose of radiation from a radioactive nuclide, such as cobalt-60 or caesium-137. It is possible to destroy the cancerous growth without seriously damaging the cells within that environment or the tissues of that patient. So the first application of radioactivity. So applications of radioactivity. You've said number one, you can be able to expose an individual to cobalt-60 or caesium-137. These are radioactive substances. When they emit their radiations, what happens? And the radiations pass through the tissue of an individual. What happens? The cancerous cells are destroyed as long as the correct dosage is actually able to get emitted into the tissues of this individual where there's cancer growth. So cobalt-60 or caesium-137 can emit radiations. Those radiations can pass through the tissues of the individual to kill the cancerous growth or to kill the cancerous cells. Sometimes surgical instruments like syringes and needles and pair of scissors can actually be able to get introduced or exposed to gamma radiations to sterilize them by killing the germs. Sterilizing surgical instruments in the hospitals or health centers can actually be able to get done using gamma radiations. Radioactive iodine 131. So iodine 131 is actually used in patients with the defective thyroid gland. Thyroid gland is found in the neck region. It actually ends up being responsible for the production of thyroxine hormone. It can also be able to have a control over growth and development of an organism or the rate of metabolism. So this can actually be able to get to that point of requiring the need for what you call radioactivity, where iodine 131 can be used to monitor the defective thyroid so that doctors can be able to follow the path of iodine through the body. You get the point? So iodine 131 can monitor the rate of functioning of thyroid gland. It can also be able to monitor the rate of functioning of this gland in terms of producing this hormone called thyroxine hormone and even the production of iodine. So at the end of the day, you'll realize that iodine 131 can actually be able to monitor the movement of iodine in the body when the thyroid gland is actually monitored. Number two, you can use radiations like gamma radiations or X-rays to determine the rate of growth of bones and the healing of fractures, which are actually internally able to get monitored. Next is what you can be able to provide power in heart pace setters. There's what we call the sinoatrial node or the pacemaker, which is just a section of the muscles in the right atrium of the heart. To monitor the power or to monitor the working of this region, we can be able to use radiations to provide power in these heart pace setters. You get the point? To actually be able to trigger the region, to trigger the heart pace setter so that it can actually be able to get kept in motion in terms of the working of the heart. You can detect leakages in the underground water or oil pipes using radiations. You don't have to actually dig up all the ground and bring out the pipe. In the oil transportation or water transportation, monitoring of the leakages in pipes transporting oil or water can get done using radiations. Now, in agriculture, you can actually have carbon-14 using to monitor photosynthesis because carbon-14 has carbon and carbon dioxide is used to manufacture food in plants. So carbon-14 as a radioactive substance can monitor the rate of photosynthesis in green plants which manufacture food. Now, absorption of phosphate fertilizers in the soil by the roots can require the use of radioactive phosphorus to determine the rate at which this can actually get absorbed. So radioactive phosphorus can be able to use this concept of radioactivity to monitor how phosphate fertilizers can get absorbed by the roots in the plant. So someone can monitor or determine the rate at which the phosphate fertilizers are able to get absorbed by using what we call radioactive phosphorus. Then other uses can be preservation of food by exposing the microorganisms to gamma radiations, which ends up killing them. This packed food in cans or tins can get exposed to radiations. All the germs in the food can get killed by the gamma radiations. So you can gauge the thickness of maybe metal sheets and maybe paper sheets, like this sleeve of paper or maybe the iron sheets. The thickness can get monitored by using what we call radiations. You can also measure the level of food which is actually in canned and packed containers. And even the amount of soda in a bottle, you can monitor the level so that the levels are the same point in all the bottles or containers. You can monitor this by using what we call radiations. You can determine the level of food in these containers, the canned food or the processed food, using radiations. You can determine the age of archaeological materials in fossils using the carbon-14 radioactive dating. And lastly, manufacturing of nuclear weapons and atomic bombs can demand the need for us to talk about radioactivity. Thank you so much, and that's the end of the topic.